Okay. So now we get into our shortcut way, because the rule that we were talking about yesterday, right? Taking the derivative using the limit method is rather labor intensive. It leads to lots of room for error. And there's plenty of other places we can make mistakes in calculus other than that. So, okay, be prepared to, on the test that you will take from me, both in now and on the final, you better be able to take the limit or take the derivative using the limit method. Okay, so now we're moving on. So what are some rules? We're going to start with the small set of rules today, and we're going to keep building on these rules for the rest of the week. So, the derivative of a constant is 0. That's nice. The derivative of a constant is 0. And just like Jimmy was saying, when we take the power rule, right? The power rule says that we are going to bring the power down in front, use it as a constant, in other words, and reduce the power by 1. And that's what we're going to be showing on these examples here. Okay, so we have the constant rule and the power rule. Now, just to kind of get used to writing these things in different ways, I want to know, what is the derivative of y with respect to x of 7? When y is equal to 7, the derivative of y with respect to the derivative of x is equal to what? 0, because it's a constant, right? Function notation of a derivative says, all right, f prime of x would be, we take the power 8, bring it down in front, and that's going to be times 2 raised to the, does it matter? It doesn't matter, does it? No. All right, so it's still a constant, isn't it? Because there's no variable right there. So it'd still be 0, wouldn't it? I fell for it. It tricked me. I'm ready to get into some variables here. So let's look at, those are the two constants. Let's look at these over here. G of x. If I wanted to know what the derivative of g of x is, let's first rewrite g in rational form. So I'm going to rewrite this as x to the 1/3. So the derivative then of g prime of x, must be, bring the 1/3 down, and then it's x to the 1/3 minus 1. You'll be doing this part in your head probably pretty soon. But 1/3 minus 3/3 is negative 2/3, right? Okay, so x would be raised to the negative 2/3 power. So we don't usually leave it like this. We don't usually leave it as a negative exponent. What do we know about the negative exponent rule? It makes it, if I change its location, it changes the sign of the exponent, right? So this would be 1/3x to the positive 2/3. And then if you wanted to go one step further, depending on what's being asked of you, you could simplify this to be 3 times the cubed root of x squared. That's g prime. Okay? Questions on how we did that? Okay. So let's look at the last one there then. It says y is equal to 1/x squared. So dy, let's just change that to be equal to y is equal to x to the -2, right? So I have a base raised to a negative exponent because I moved the base. So dy dx is going to be -2 x to the what power? -3. Or in other words, -2 over x cubed. All right. So when we're dealing with radicals, you want to change it into a rational, right? You want to change it into in its rational form. And then typically, for now, if you just have a single variable down there in the denominator, so it's easier to rewrite it using the negative exponent rule, apply the property, and then go back to the written form of it. Okay. Find the slope of the graph of the function f of x is equal to x to the 4 when x is equal to -1 and when x is equal to 0. So in other words, if I wanted to know what the slope of the function is to the graph, or the slope of the graph, that's basically finding the derivative, isn't it? Okay, so f prime of x is going to be what? Bring our 4 down. We have 4x to the what? 4x to the 3rd power. That's the function for the slope, right? Of any line, any point on that graph. And we want to know what is that value when x is equal to -1. So evaluate the derivative at -1. And what do you get? -4. F prime of -1 would be 4 to the -1 cubed, or -4. F prime of 0 is going to be 0. Okay. All right. Fairly straightforward, the ones that we're going to cover today. We have another rule that's just basically an expansion of what we're talking about. It's just the constant multiple rule. Basically, if I wanted to take the derivative, then I can pull the constant out front, take the derivative of the function, and then multiply the constant back by that. Okay, remember that number in front is kind of like a scale power anyway. So we're going to take it out to the front, take the derivative, and then multiply it back in. So what we're looking at here says dy dx would be equal to, I'm only going to write this once, it looks like 7 times dy dx of x cubed. That's kind of a different way to look to write the derivative. I don't always like it. It gets kind of messy. What it's saying is the derivative of y with respect to the derivative of x is equal to the constant 7 times the derivative of y with respect to the derivative of x cubed. Okay, that's what that says right there, if you ever see it like that. Now, in other words, take the derivative of x cubed. So we have 7 out here. The derivative of x cubed is what? 3x squared. So then the value would be 21x squared when we simplify it. Okay, let's look at the next one. Let's look at together. Let's do C. Right. So I'm gonna skip around on these because I'm gonna let you all do some of them. So I want to know what is the derivative here. F prime of t looks like 4/5 times t squared, right? 4/5 times t squared. Pull that constant out. So now I have 4/5 times 2t when I take the derivative. Or in other words, 8/5. 8/5 times t. So I wanted you to see, because we want to kind of, I had a constant there, so I can just kind of separate those out like that. Let's together look at G. Let's do G together. So I have y prime is equal to 5/2 times x to the -3. I pulled the constant out and I took the base and rewrote it, giving me 5/2 times -3x to the -4. Or in other words, -15 over 2x to the 4th. Are we all right with what I did there? So I took my variable, moved it to the denominator because it was negative. 2 is already in the denominator, so I put it down there, put it back down there. All right? Okay? All right, let's look at E together. So we have y prime is equal to 1/2 times x raised to the what power? Positive or negative?
Negative.
Negative 2/3. Okay, do we remember that? Okay. So I have 1/2 times -2/3 x to the, what would that be, 3/3, so that'd be -5/3. -2/3 minus 1 would be -5/3. Okay. So I would have, these 2's are gonna cancel, so I'm gonna have -1 over 3x to the 5/3, or 3 times the cube root of x to the 5th. Okay? Okay. So on your paper, you have 4 to do, the 4 remaining ones. Come back here. This is the. This is right. So this negative doesn't go here. So that's like saying -1. And you didn't have a negative. You have, when you bring it up, you have the exponent is -1. So now, what do I do here? I bring. So now it becomes negative. Well, this one's not correct.
No, not you.
No,
Oh, Lord. Where is it?
you didn't really do anything.
I didn't do that.
No? So all you do is write x to the -1, correct? You converted this to 2 times x to the -1, right?
Yes.
So that's not taking the derivative, that's
No.
just rewriting it.
Yeah, that's all we did up here, but I didn't know it was going, I wasn't it. So I don't know.
All right, so the rule, do you have the rules written down?
No, I didn't know it just.
Okay, so the rule says you're just gonna take the power. Yeah, write down x squared. Write down y equals x squared. Alright, so the power rule says we're gonna take this exponent, we bring it down to the front, so it becomes 2 times x to the 2 minus 1. Exponent minus 1. Always reducing it by 1. Okay? So then this becomes 2x, right?
Yeah.
That's the derivative. Right? This is equal to y prime. But y prime equals this. That's the rule we're following. We're subtracting by 1. So if this is x to the -1, put x to the -1. Right? So this is surrounded by parentheses. That was correct. So how do I apply this rule? The exponent comes down in front. -1 times x to the -1 minus 1
Yeah, okay. Okay.
times the 2 that you already had. And write it without a negative exponent. So
Oh, yeah, yeah.
one step further. Got it? Yes. Similar answers? So this is -1.
Yeah.
The -1 Okay, so that's gonna change the sign to be negative, right?
Because it's -1/2.
And then that was correct. It becomes -2. -1 minus 1 is -2. Okay. So now, negative, this is just simplified, -2 times -1. That x is gonna move down to the denominator.
The negative one.
So why you put this down here before the rule
This is
is,
like.
so this comes in front, and then you're subtracting it by 1, right? That's the rule.
I'm lost.
This part.
It is.
This would have to be 1/2 the square.
No, it'd be.
So you put it in the denominator, but it's not a square, it's a square.
Oh.
Right.
Yeah.
This one is.
There's no more. Was that right? Go check it.
Because it becomes negative
Oh.
1/2, right? The negative.
Oh, yeah.
right?
That can multiply, so it's.
And then -1/2 minus.
Oh, it was. Wait, why is it negative?
What'd you get, number 2?
You're right, you're right. So
Okay.
it's 2 times, so it's X. So
Yeah.
that minus 1, no, I agree with that.
Wait.
And that would be 1,
It's
correct?
negative 1, you bring it down. you multiply by
And this is right.
Yeah. That's correct.
It is today.
I was looking for this
Oh.
written out, that was what I was looking down here.
The one I have.
When I was following your work, as my fault. Okay, do you have answers on all of them? No, you're still working on them?
First one I got negative 2 X. Well, then this group of X. X. Yeah, so start with that. I'm trying to do stuff. That's why. I don't know.
You get one.
See, how do you do that when I don't write up the steps? You're gonna separate the concept and
I was.
separate yours.
I
See, on
mean,
four-
one of them has to take the negative value.
Look at-
It just means if they both have the value.
Well, look at. Now they distinguish the T out, not just 3. 14. Can you agree with them?
Yeah.
That's what I was looking at.
Oh. I mean,
No, that's right.
That's-
Why is it
It's
easier?
outside of negative 3 has, like, if you
Yeah.
multiply. Yeah, so she just. That's like.
That is it.
After
So you do simplify this all the way down.
Linear to a constant, right?
How can-
It's 4 hours.
Okay, I know.
Why is that?
Yeah.
It was X to the 1. So 1 minus 1 would be 0.
Photo man. That would be. Square.
Since it's in the bottom.
We're up to the next.
So, yeah, so then you cancel, so it's No, not about.
You good?
Yeah.
Well, this is the same thing. So it's almost like. distributed property. Actually, everything up. Right, and it becomes 7 times 3 squared.
So I found.
Did you buy it?
No. One shot. It's the exact same. Yeah. It's so weird, like, why would I need to do that?
All right, are we good? Oh, okay. Okay, make sure your answers are the same as what we've got going on up here, right? These are fairly straightforward. You just gotta kind of take them in pieces, okay? So the next one that we're gonna do, does anybody have any questions over these? No? No questions? So I don't know if I'd write this rule down, okay? I don't think I'm gonna ask you for this rule. This rule is basically just saying, kind of like the constant multiple rule, right? I could take the constant out, take the derivative, and then multiply by the constant again. This is just saying, okay, well, if I'm taking the derivative of f of x plus g of x, then I can individually take the derivative and then add them together, all right? So think about polynomials like you see here, okay? Or think, notice that question C down here, or letter C down here, this is a rational function, but the denominator is only, I'm going to be able to use division, in other words, on that. All right, I'll show you what I'm talking about on that, if we wanted to do them individually. Now, this is fairly handy. This just kind of approaching each of the terms individually is what we're asking here. Because we'll see tomorrow when we use the product rule that sometimes it might just be easier to use this rule. So we have the y is equal to x cubed minus 4x plus 5. And the derivative of this, right, y prime says, all right, the first term is just going to be what? What's the first term, everybody? 3x squared. Minus 4. And then I'm done, aren't I? Because 5 is a constant. Yeah? Okay, that's easy. Okay, we had a cubic function reduced down to a quadratic function, didn't we? All right, kind of straightforward. Let's look at the next one. F prime of x looks like a negative 1/2 times 4x cubed plus 3 times 3x squared minus 2 times 1. Simplifying that, we would have, what, 4 to the third power? No, not 4 to the third power. That would just be, because I'm not raising it to the third power, it would just be -2, wouldn't it? 1/2 times 4x cubed plus 9x squared minus 2. Y'all do group me's? Y'all have any of those group me chat thingies? I'm in a group me. I hate it too. Okay. Y'all don't do the group me's? Really? You don't have any classes that do the group me's? Huh?
I can basically just names, but I didn't know.
Because my kids are both, they're both in, they use group me's all the time where they're at school. They all talk about it. The teacher. Okay, the last one. So for this one, if we approach it using this method where we're going to kind of look at each of the individual terms, then I can look at this and I can say, okay, g prime of x would be equal to 3 times x squared over x minus x over x plus 1 over x. I'm just simplifying here. Leaving me with 3x minus 1 plus 1 over, plus, I'm going to change that, x to the -1. So the derivative of 3x is just 3. The derivative of a constant is 0 plus, what would we have? -1x to the -2 when I take the derivative of the last term. So this is 3 minus 1 over x squared. Okay, questions on that? Now, like I said, when we look at the product and the quotient rule tomorrow, here I've done the quotient, I've done a simplified version. I'm not actually applying the quotient rule because I was able to take each one of these individual components, reduce them, and then address them as the derivative in each single one, okay? And that might be a little bit helpful. All right, the last one as far as derivative rules that we're concerned with is the derivative of e. This one's always easy. What's the derivative of e to the x? There you go. Derivative of e to the x is e to the x. Yep. Okay, it becomes a little more difficult when we have something up there in the power position of e, right? That's going to be Thursday. But for right now, this is fairly straightforward. Y prime of 3e to the x would be 3e to the x, wouldn't it? 3 comes out, the derivative of e to the x is just e to the x. So f prime of x, what's the derivative of x squared? 2x. What's the derivative of e to the x? There you go. 2x e to the x. Okay. Now, let's look at a couple, I think 2. Application type problems, and then y'all are going to do some work for me. So we're talking about rates of change here in these 2 problems here. And for this first one, it says the position of a small rocket is launched vertically upward and given by the function s sub t is equal to that for time between 0 and 10 seconds. Okay, so a couple of things that I want to point out to you. Anybody taking physics in here? Or is that next semester? Next semester? How many of y'all had physics in high school? Okay, you probably know most of this stuff, so we won't go too far into this. All right, so we are considering this function here is considered the position function. All right, it's considered the position function. It's the normal quadratic function you started out doing whenever you did quadratics back in Algebra 1. Okay, so this is the position with respect to time. WRT with respect to, right? It's the position of the rocket with respect to time. All right, now, the derivative of the position function is actually equal to the velocity with respect to time, which is the change of the position function with respect to the change of time, or the derivative of s with respect to the derivative of t. So you have your position function, you have your velocity function. What comes after velocity? Do you all know?
Speed.
Velocity and speed are the same. Well, speed is the absolute value of velocity. Acceleration. Okay, acceleration. All right, and so acceleration then, the derivative of velocity is acceleration with respect to time. Okay. So this is called the position function. This is velocity. This is acceleration. We're not really doing acceleration today. We're doing it tomorrow, but that's how they're kind of related, okay? So in this particular question, it says, find the rate of change in the position of the rocket. Find the rate of change in the position of the rocket. That question is basically asking you, if you're finding the rate of change of the position, then you're finding the velocity. Finding the derivative of the position function. So the derivative, which again is equal to the velocity of negative 5t squared plus 40t plus 100. So what's the derivative of negative 5t squared? Negative 10t. What's the derivative of 40t? 40. Plus 40. So the velocity function, or the rate of change in its position, can be found by the velocity function, which is negative 10t plus 40. That is actually instantaneous velocity. That's what they're talking about instead of average velocity, if you ever see that. Instantaneous velocity would be the derivative part, okay? Instantaneous. Now the next part of this question says, okay, well, at what time is that instantaneous velocity 0? So when is the function itself equal to 0 is what I should say. So we would have negative 10t plus 40. What time would it be at when that velocity is equal to 40? Right, 4. So we would say 40 is equal to 10t, or in other words, t would be equal to 4 seconds. Okay. And then if we just wanted to look at this one here, we could graph both of these functions on the same graph, which looks like this. So the red line right there, the red line represents the position function, right? The black line represents the derivative. That represents the velocity, okay? The black line is the derivative of the red line. So both of them would be on there. And the question that it was being asked said something like, what was the magnitude? When does it have the greatest magnitude? And what we're kind of looking at here is, you can almost see that this would have, if we are down at negative 60, so then that would be the greatest speed. Above that would be 40, wouldn't it? That's what I'm looking at right there. Did y'all know there was a Formula One race in Austin this weekend? That was kind of cool. My kids went to it. That reminded me of that, just that part right there, speed. All right, so you can just graph those two things right there. Now, what if we have another question, because we have another one that we want to look at that'll be similar to this on your problems you're working on. Again, with our position function. From the graph, we can see how the speed changes with a max speed. So the maximum speed of the graph that we were looking at gave us we found from the derivative, it looks like it was 60. Okay. But I might have to go back and look at that again in just a second. But I want to look at this one really fast right here. This one says if the position of an object in any time in hours is given by, once again, that cubic function, we want to determine when the object is moving to the left. So for these position functions, the velocity or the derivative of the position function, which is given by, which we understand to be velocity. Velocity is also considered a vector, right? Yeah, okay. So what we're gonna look at, we're gonna take that idea about the vector and we're gonna find the derivative of the position function, all right? And then we're kind of determining out of that, I think of it in terms of a vector, I suppose. From that, we're gonna determine where the function is positive and where it's negative. I'll explain it in just a second. All right, so let's start by taking the derivative of our function. So if I have the derivative of this, s prime of t, then I'm gonna get, what would I get for that first term there? 6t squared minus what? 42t plus 60. All right, that is the derivative of the function. And what I want to know is I'm going to set this equal to 0 because I'm interested in where the function, where the derivative is positive and where it's negative. All right, so when it's positive, we're going to be moving to the right. We'll consider that a right movement. And when the derivative is negative, we consider that moving to the left. All right, that's how we're kind of looking at this. So if I set this equal to 0 and solve, I'm going to factor a 6 out of that, and I get t squared minus 7t plus 10, or t minus 5 and 2. Okay. So I know that the derivative function has x-intercepts at 2 and 5, correct? So this is why we practice this a lot during our polynomial and rational section. So here, I'm going to come over here and I kind of want to zoom in on the x-axis. So here's the derivative. And I want to test some points to the left and to the right of 2 and 5. So when I'm to the left of 2, what are we going to get? Just positive versus negative.
Positive?
And when I'm between 2 and 5, I'm going to get
Negative.
negative. And then I'm going to get to the right, I'm going to get
Positive.
positive. So what we're looking for here is we want to know where the derivative is positive versus negative, because positive implies movement to the right, negative implies movement to the left. So the object would be moving to the left between time 2 and 5. That's what that question is asking. Okay? That's all we're looking for here. Okay. So the last thing, and I'm not, I feel like I had one. We'll make one up. The last thing I want to talk about is higher order derivatives. So just like we said that we had our position function, and then the derivative of the position function was velocity. And the derivative of velocity was acceleration. Then that must imply the second derivative of the position function is acceleration. Okay? So what we have here are what we call higher order derivatives. In other words, you can just keep taking the derivative. Just keep on doing it, okay? As long as the derivative exists. So, let's take that one we were just looking at. If I had, and we'll just call it S prime, S. So we had S, which was given by 2t cubed minus 21t squared plus 60t minus 10. The first derivative, S prime, we said was 6t squared minus 42t plus 60. The second derivative, S double prime, would be 12t minus 42. The third derivative would just be 12. And I can't go any further, can I? You just keep taking the derivatives and you keep adding tick marks up there. That's about it, all right? You'll have a couple of questions like that on your homework, where you have to take the derivative and then take the second, maybe the third derivative. I don't think so, but at least through the second derivative. Okay? All right, so we're gonna take some time to practice these things.